Okay, 3.1 Modeling with Linear Equations. Occasionally we will be given either like word problems, that kind of stuff, and you'll be asked to come up with a linear equation that would express that. So in this case it says we have some new office equipment, $2,500 per machine. The company chooses to depreciate each machine using the straight line method over 5 years. So there are a couple of things here that we need to be familiar with. First of all, the word depreciate means that another way to say that it would be to devalue or to make worth less. And when they're saying straight line method, the straight line has a constant rate of change. So what they're implying here is that a machine that costs $2,500, if you want to depreciate that in 5 years, you're going to make it $500 less or worth less each year. Alright, so build a linear model that expresses the value of each machine as a function of its age. So the value based on the age is, well, right now they're worth $2,500 each, and if we're depreciating in 5 years, then we just saw that we are going to subtract $500 for each year, and that would be the equation. The implied domain is, well, right now it's year 0. We're doing this in 5 years, so from 0 to 5. Probably should have a square bracket around those because you can get to 0. So let's make it this way. Alright, graph the linear function. Okay, so this one's fairly straightforward. They're not always that easy, so let me pick sort of an easy example. But let's see, 2,500, so 500, 1,000, 1,500, 2,000, 2,500. And that would be value in dollars. And then here it's age in years. So 1, 2, 3, 4, 5. Starting here, there we go. Interpret the slope. This is sort of a standard line that you need to learn. So interpret the slope would be for each change of, let's actually look at the number. This says 500. And think about it as 500 over 1. This was $500 per 1 year. For each change of 1 year, each machine will decrease in value by $500. And when will the value of each machine be $500? And you can probably see this sort of without having to do it, but they basically want you to solve this. And hopefully, when you guys do that, you get 4 years. Okay, one example. Different example, a little bit more complicated. We have 2 equations here, and I guess we're dealing with supply and demand. So the quantity supplied of a good is the amount of a product the company is willing to make available at a given price, and the quantity demanded is the amount of product the consumers are willing to purchase at a price. Suppose that the quantity supplied and the quantity demanded of cellular telephones each month are given by, and then we have 2 functions. What are we being asked to do? Let's see. The equilibrium price is defined at which quantity supplied equals quantity demanded. So I even wrote the equation for you there, and we need to find that. Well, they're sort of nice to us here. They literally told us what to do. Those 2 things are equal for only 1p, and that's the price that we're interested in. So move this across, 75p P equals, move that across, 37.50. Divide by 75. So I think the price we're looking for is 50. And then we need to find the quantity at that price. I'm probably out of room over there, so we'll do the second one here. The quantity on that price would be, well, we can find it two ways. We can use supply, which in this case is probably easier, because 60 times 50 I can do in my head, minus 900, which is 3,000 minus 900. So the quantity is 2,100 units. And we would have been able to find that also by using the demand form. Okay, determine the prices for which quantity supplied is greater than quantity demanded. Alright, so when is quantity supplied greater than quantity demanded? Well, so basically you're solving this one again. And you have 60p minus 900. And that needs to be greater than negative 15p plus 2850. So p greater than 50. You also could have done that from a quick sketch, but I'm going to skip the sketch because it just saw here that we actually need to do a graph. So there is a difference between a sketch and a graph. So we'll see that here in a second. So what can we do here? Well, you could do this sort of by hand, and you draw your axes, and then you take a look at the two things you're trying to graph, which are these two things. So 2850, that's pretty close to 3,000, so let's say that's 3,000. So 1, 2, 3, so that's 2,000. That would be 1,000, so that's quantity. And then we're going to put price here, so quantity is here. And then price goes over there. And we need to go out to 50, so 10, 20, 30, 40, 50, 60. And we know that at 50, we are at 2,100. So that's one dot at the share. And then we would need to find another dot. Well, we could sort of eyeball this one. So, yeah, it's 2850. So that would be one way to do it. And then the other one, 60p minus 900, so a negative 900 would be something over there. So we're going to just eyeball it, except we'll start, I guess, close to 20. Does that make sense? So let's see. So I'm curious to see where I'm crossing. So 60p minus 900, I want that to be 0. So 60p is 900. P would be 900 divided by 60. That's 90 divided by 6, so that's 16. So that's pretty close to 20. So we'll call it 16. So, and there you have graphically a picture of what we were talking about, and you can see that the quantity supplied. So this is our supply, and this is our demand, and that at this point, 50, 2,100, they're equal. Everything above it, supply is larger. Everything below 50, we actually have more demand, and that takes care of that. We could have done that with a graphing calculator or with GeoGebra, and but you would be able to find it a little bit easier and manipulate the graphs probably a little bit easier. So that's a second way that you can do that. Thank you.